Hello, Dr. Tangabal Murugan. Are you able to hear me?
Yeah, good morning.
Good morning. Well, first of all, thank you for agreeing being this session chair for this one. Just to remind you, since this is going to be first session, some people maybe a little bit late. I suggest that if you can wait maybe 2 or 3 extra minutes before you
Yep.
start, that will be nice. You can go with the order of the paper IDs, but if an author is not available at the moment, you may just skip and then go back and ask if they join the session a little bit later. At the end of the session, please conclude the session with your own remarks, and then please send us an email specifically indicating the best presentation among the group, along with if there is any paper that's not been presented, please let us know the paper IDs and paper titles, okay?
Sure, sure. Yeah,
Okay, thank you so much. Good luck.
yeah, thank you. Yeah, good morning, everyone. Um, we will start in a few minutes. Okay, we will start in 2 minutes. Please be ready with your presentations. Good morning, everyone. Welcome to our session 12, day 2 of ISDFS 2026 conference. Myself, Dr. Tangvel Murugan from United Arab Emirates University, and I'm going to be the session chair for this particular session 12. As you see, we have 7 papers scheduled on this session. So, first, I'd like to welcome Niranjan Pachayappan. Uh, to present your paper ID 98, GenReach AI, an agentic generative AI framework for automated reachability analysis of enterprise software vulnerabilities. So before you start, a common instruction to everyone, please do your presentation in first 10 minutes and then we can have a Q&A session. Over to Niranjan Pache.
Good morning. Welcome you all.
Yeah, good morning.
Uh, can you guys see my screen? Just give me a second. Let me share my screen.
Yes, your screen is visible. We can see your email. Yes.
Can you see my slide?
Yes.
Okay,
Please
thank you.
proceed.
So good morning, everyone. I'm Niranjan Pachayappan. I work as a Chief Cybersecurity Engineer at Visa Inc. In today's presentation, I actually have 2 papers. The first one I would like to present is related to reachability analysis with open source vulnerabilities with the help of generative AI and LLMs. Open source vulnerabilities is actually a very common security issue that a lot of organizations face nowadays. Any application or any platform that any company creates has open source libraries embedded in them, and most of the open source libraries have a lot of security vulnerabilities associated with them. So in this paper, we are going to talk about what is the motivation behind such a generative AI system to basically figure out if a particular vulnerability is reachable or not. So what we have identified, as well as what we have going to present in the session, is that in terms of industry, the overall industry, there is definitely a gap in how all the automated scanners review and scan these vulnerabilities. There are a lot of false positives which results in a lot of time that is spent in figuring out whether it should be vulnerable or not. So what we have done is that we have taken a set of applications in production, around 500 microservices. We actually channeled that through our system, which is going to be the GenReach AI system. This is a 3-layer vertical architecture of it, where there is an ingestion layer where we ingest all the artifacts associated with the application or the ecosystem, such as your infrastructure as code templates, as well as your code repositories, and as well as the software bill of materials. And then creating this knowledge base, we'll then feed it to a set of agents that will work in cohesion, which is going to be a reachability agent or context agent. Again, the names doesn't matter. It's basically the set of agents with context aware reasoning that will determine whether that particular vulnerability is reachable in the ecosystem or not. Then we have our enforcement layer, which is a typical software development lifecycle where we can plug that into a developer-centric pipeline or continuous integration and deployment pipelines, as well as auto remediation pipelines. In terms of the specialized agents that I was highlighting as part of this particular paper, the inventory agent, as I was highlighting, will take care of all the literature related to what that particular application is about, what those open source dependencies are, their associated CVEs, which is publicly available data. Then the context agent will get the actual deployment details of that particular application in the ecosystem that it is deployed in. So we'll be able to know what the ingress and egress points are. Then the reachability agent, which will perform a tree graph analysis or a tree sitter analysis, depending on the language or depending on the programming platform that is used. But what it will do is that it will basically figure out and create a map of all the associated functions and methods. Then the verification agent, which will perform an exploitability check. So this is a high level overview, not diving too much into the details, as folks are probably aware about what MCP is and what Gen AI is. So this is basically the implementation details of the platform that this paper discusses, where the orchestration layer, again, this paper is like probably like few months old, but there are other orchestration layers nowadays that is present. But in this paper, we use LangGraph. We used Tree-Sitter, GON, and CodeQL for the container analysis and code analysis. We also use Langsmith and other stuff for optimizing the performance of LLMs and agents. And then we used the GPT-4 model, which was the top model available at that time, and 3.5 Sonnet for code generation and code-based reviews. We also used a ChromaDB, which will embed all the CVE metadata in it. This is a high-level overview of the agentic workflow sequence that we are proposing in this paper. Once the orchestrator is like initiated, it will fetch the inventory details, all these agents like contacts and reachability. Then finally, the verification agent will basically give a response of whether it is exploitable or not. If it is exploitable, then the alert of prioritizing for remediation will pop up, or if it is not exploitable, we can suppress it from our overall reporting pipelines. So this is the evaluation setup that is discussed in the paper. As I mentioned, 500 microservices, variety of different programming languages and platforms. We also did 3 implementation modes for this particular agentic pipeline. We integrated this pipeline in the CI/CD phase. We also integrated this in our real-time runtime phase, where we monitor the live traffic and WAF rules and WAF metrics. And also we integrated into developer-centric platforms like the code generation IDEs, where they'll be able to basically perform the reachability analysis while they are developing their application. And we did compare this particular approach to the existing traditional software composition analysis or reachability analysis tools, and we are proposing what are the results of it, and as well as the benchmarks that we were able to perform. So this is our performance results. A traditional SCA, which is any type of open source vulnerability scanner, has a false positive rate of around 48%, which is clearly nearly half of all the findings that are remediated, all findings that are flagged, as well as it takes around 12 hours to triage each and every vulnerability. But with the help of Genreach AI agentic framework across 3 different implementation pipelines, especially a real-time pipeline, we show that the triage efficiency increases around 9.2x, as well as we are able to reduce the false positives by 87%, 87.5%. So this is our overall benchmarking with baseline, real-time, and recall features. So we were able to get a 0.97 recall for accuracy, as well as we were able to reduce the overall false positive results. The operational impact obviously is that the more noise the scanners produce, the more fatigue the developers and the organizations get in remediating them. With the help of this particular agentic workflow, the organization or developers can basically reduce the amount of time they spend on remediating or even like triaging vulnerabilities. So we did a couple of case studies in this paper. Log4j, which is like a popular logging framework with Java, had a 0-day vulnerability 5 years ago. Recently, React to Shell, which is one of the frontier front-end frameworks that is available for development today, it also received a 0-day vulnerability last year, which was very popular. So we did a case study on these systems, and we basically, the agentic framework was able to show that one of the critical vulnerabilities was not reachable or not exploitable. So in this case, the remediation can be like deprioritized based on risk, and whatever is like the exploitable vulnerability should take precedent of it. And we were able to do it at scale as well. So this is a couple of case studies that are presented in this paper. On top of our context map, so we are also like done environment aware scoring, so that way the business leaders as well as the product owners are also able to understand what is the actual cycle it takes for remediating these things. The future work that we are discussing is that definitely there are a lot of benefits to agentic frameworks, but the future work has limitations as well, where the cost of LLMs have to normalize. Right now, they are around like $2 to $5 based on what we've experienced in our evaluation for each microservice scan, as well as the amount of hallucination that these LLMs produce. So it has to be fine-tuned, the model parameters have to be adjusted accordingly, as well as there is like initial technical friction in terms of setting up all the orchestrators, pipelines, and whatnot. There is cost associated with that, as well as technical acumen required for doing that as well. The future work that we are exploring with this particular agentic workflow is that we'll add additional vulnerabilities that are more prevalent in the industry, and see if it is possible to create a set of exploitation scenarios that can be validated in real time with the help of generative AI. So at the end, the value that we are proposing is that this will definitely help with reducing the overall development time, or in an industry context, not just academic. In industry context, it will help organizations deploy and secure their applications faster in a better manner. So that's at a high level what this paper is about. Any questions?
The floor is open for the audience. Any questions? So I have one doubt related to the work that you have presented. Really, it's a good work. The basic idea is to bring the generative AI into the picture to automate the vulnerability identification, right? So it also analyzes the severity of the vulnerability or just the detection of vulnerabilities.
So it starts with deduction. So typical SCA scanners do a signature-based validation. What they do is that they'll decompile the application, they'll fetch the artifacts that are like mentioned in the application, then they'll compare it against a known database, saying that, oh, this particular library X has this particular version Y, this particular version Y has a known CVE, and they flag it. So it's mostly like a dashboard of sorts. So what a context-aware agent that we are proposing here, what it does is that it not only does the typical deduction work of any of the tools that are available in the market, it also brings it basically takes all the parameters associated with it, whether it is severity, whether it is the function or the actual attack path that is mentioned in the CVE, as well as the different prerequisites or the setup that is required for a successful exploit to happen. So it takes all that plus the actual deployment environment into context, then proposes a score or proposes a flag that says that this is indeed an actual vulnerability in that particular implementation. That implementation may use that library but may not be vulnerable. So instead of development teams spending time on patching or fixing something, it would basically improve their overall efficiency, if that makes sense, Professor.
Great. Thanks for your time. Now we can move on to your next paper, ID 108, Systemization of Privacy Threats and Defenses in Modern Agentic Web Browsers. Yes,
Yeah.
please.
Thank you, Professor. So the next paper that I would like to propose is also in the generative AI space, as we become more adaptive to the overarching industry where generative AI is penetrating into most of our day-to-day life, as well as most of the organization's pipelines. There is one area that we've thought that we would cover in this paper is agentic browsers. And as more and more agentic browsers are introduced or developed, the privacy concerns associated with them definitely needs to be reviewed. And in this paper, we are actually gonna do a systemization of all the threats that we think are relevant, as well as the defense mechanisms that needs to be incorporated in order to preserve the privacy when adopting or when developing these agentic browsers. So typical comparison between a regular browser, like any browser that we use today on a day-to-day basis, like Chrome or Safari and whatnot, its primary purpose is to basically fetch content, present that content to the user. A lot of browsers have inbuilt security for sandboxing, site isolation, cross-domain references as well, and it also helps preserve the user control, where user dictates what they want to see, whether they want to go to a particular website or not. There are a lot of different browsers out there today, even privacy preserving browsers in the market like DuckDuckGo and whatnot. Those are mostly user controlled or user centric. The agentic browsers are something that is new to the industry, where there is autonomous execution, where it basically requires the full control over the user's intent as well as user's content. Then it makes autonomous decisions on top of what the user's preferences are, without the user interference. There is a lot of positive use cases to use agentic browsers, even with all the new advancement and open source technology like OpenClaw or NVIDIA announcing NemoClaw. The agentic workflow is going to be the future, but the privacy concerns is that is that they must bypass the traditional security boundaries that has been defined so far. So some of the high-level browsers that we've evaluated and looked at in this particular proposal is OpenAI Atlas, Google Project Jarvis. Anthropic Computer is not really a typical agentic browser, but it is an agentic workflow that has API access, that has file system access, as well as the browser company's DR browser. So some of the high-level stuff that we are showing in this paper is the taxonomy of threats, a formal threat model, a multi-layer reference approach, as well as what evaluation frameworks we use, as well as what could be the future implementation roadmap on top of the regulatory requirements that may come across. So this is the high-level architecture of an agentic system, agentic browser. From a overall standpoint, the threat actors may inject themselves in various stages of the agentic browser execution, as we have shown here, where they can either compromise a user's device, or either they can compromise the backend, which infers all the user's content and uses LLM, or any third-party integrations. For example, the agentic browsers can make payments and whatnot, which would integrate with certain payment providers. So we identified some of the threat vectors associated with this particular architecture, and we also compared what is the risk associated with data flows. For example, if we look at OpenAI Atlas, the data flow is basically dependent on cloud inference, which means that the threat vector is going to be the backend. In terms of Google Gemini, it's basically about the overall collection of private data without the user's consent, as well as the DR browser, which is basically saving a lot of data within the browser memory, which could create extraction point, going back to the user level extraction. There are a lot of hybrid designs that are coming up where they basically say that they don't need to have user consent, but just need the user's DOM access. So we've also talked about this in this proposal. This is the taxonomy of threats that we have identified based on known industry standards. Some of the threats are well known for regular security work. We've also kind of mapped it to the privacy risk of agentic browsers. So the prompt injection, as well as exposure, supply chain risk, all of those things do come into play. This is an example of how a memory-based inference attack sequence would work, where any application that kind of has the memory persisted with the agentic browsers would be able to use that data to go to the LLM inference engine, but an attacker would be able to either mimic or spoof the user, or they'll be able to compromise the inference engine, basically able to get the full details and privacy conditions of that user. So this is one example of the inference attack. There is also prompt injection attack, where for example, I wanted to visit google.com, but if there is a hidden malicious site in the agentic browser where it executes an attacker's website, then they'll be able to extract the data that was supposed to go to a particular website that I pasted. So this is an example of that, which we talked in detail in the paper as well. Skipping over the next phase, this is the common stride taxonomy that we use for classifying threats in a classical threat model. We've applied that to the agentic browser privacy issues as well, where the leakage of browsing history could lead to information disclosure. The third-party plugins could lead to tampering, as well as if every action is anonymous, then there could be a repudiation impact as well as audit impact to the overall execution of tasks. And if the browser is susceptible to prompt injection, then it could also lead to privilege of escalation, which we've seen in the past, where a lot of these adoption of new frameworks like OpenClaw, we see that people having issues with full autonomous access, and their email box is being deleted, or their database is being deleted and whatnot. We've also did an extended analysis in this paper using the Mastro framework, which would take the agent or tool or environment which is associated with the agentic browser into context as well. Long story short, we discussed some of the core aspects of it, and also we highlighted what could be the typical violation in terms of regulatory landscape that we are looking at with this ever-growing agentic browser ecosystem. GDPR is definitely affected, CCPA is affected. There is also some sort of sovereign cross-border issues where the data could be traversing between different sovereign boundaries, which we are not supposed to happen in the typical privacy realm. And right now, based on what our systemization of approach is, that we didn't see a privacy by design approach in most of these major browsers. So which is what we are basically proposing in the defense layer, is that we can use either a cryptographic or a behavior anomaly type of defenses to basically address some of these privacy issues, as well as we can utilize the current availability of full homomorphic encryption frameworks, which again has its own limits as well, which we've discussed in this paper at length. But this definitely provides an additional layer of privacy on top of the current default behavior. We also showed some evaluation metrics as part of this paper, which is mentioned in table 4. What is the privacy leakage rate, exposure rate? We did a quantitative as well as qualitative analysis. We also showed a phased implementation roadmap on how a secure agentic browser can be developed or deployed. Some of the open problems we've discussed in this paper is how we can enforce homomorphic encryption for LLMs. Is it possible to get that? As well as, is there a scalable anomaly detection platform? In terms of industry standards, is there like adoption of new and growing protocols that certain industry leaders have launched, certain industry competitors have launched? So that is what we have discussed in the future paper. The conclusion is that the challenge definitely exists with the adoption of agentic browsers and users pivoting more towards autonomous decisions. In this paper, we've contributed the taxonomy, formal threat model, as well as defense strategy. The path forward is that the industry has to adopt standardized frameworks and protocols, which is going to be evolving over a period of time in the near future. But we wanted to see if there is a way for us to classify that. So that's it with our paper today. Any questions?
Thank you. The floor is open for the audience. Any questions? Okay, fine. Thanks for your time and thanks for your presentation.
Yeah, thank you very much, Professor. Appreciate it. Thank you.
Let us move on to the next paper, paper ID 158, Modernizing SAP Business Objects Using Enterprise Data Warehousing Principles by Prashant.
Okay, hi. This is Prashant here. Hope you can see my screen.
Yes. You have 10 minutes. I can
Sure.
remind you of the 8-minute. Thank you.
Sure, yeah.
Please proceed.
Yeah, so myself, Prashant Satyabalan here. So this is in regards to modernizing SAP business objects using enterprise data warehouse principles. And the contents that we are going to cover is the abstract, introduction, literature overview, research methodology, results and discussions, and conclusion references. So the abstract is like the traditional SAP business objects environments were largely built on OLTP schemas that were incrementally modified to satisfy short-term reporting needs, resulting in complex and less maintainable reporting structures. The study proposes a warehouse-first modernization strategy that redesigns the data warehouse using dimension modeling with centralized fact tables, confirmed dimension, and surrogate keys. The analytical model like OLTP warehouse aligned star schema were implemented in Power BI using identical dashboards, measures based on global store dataset for the fair comparison. Evaluation was based on the join complexity, refresh time, visual rendering time, analytical consistencies, and the time intelligence support showed significant improvement with the star schema model that we have used. The star schema reduced the join complexity around 60%, improved refresh performance by 30 to 50%, provided faster visual rendering compared to the OLTP models, centralized measures and dedicated data and date dimensions, enabled consistent and reusable time intelligence calculations, while warehouse first strategy improved maintainability, simplified universe, ensured the consistent business logic and security implementation across the platforms. So this is the introduction. So many SAP Business Objects environment were built on OLTP schemas, wherein these schemas gradually expanded to meet the reporting needs, resulting in complex semantic layers, inconsistent KPIs, and slower reporting performance. The upgrading to BI platforms alone did not resolve these issues, as performance and migration challenges mainly arise from poorly structured underlying data models. A warehouse-first modernization strategy reorganize enterprise data using data modeling concepts such as centralized fact tables, confirmed dimensions, standardized measures. This approach improves query performance, simplifies semantic layers, standardized KPI calculation, and provide better support for advanced analytics and time intelligence across BI platforms. The study compares OLTP-based warehouse aligned star schemas models in Power BI using global store dataset to evaluate improvements in performance and consistency and migration readiness. So this is a literature overview wherein the methodology form used by various authors that they had used here. So basically with the Kaggle data set warehouse optimizing query, optimize OLAP analytics path route scheduling algorithm, and findings were improved inventory management, order packing, and shipping efficiency through warehouse optimization. Limitations case study may not be generalized across industries. Further work explore integration with real-time IoT data to predictive analytics. So, like as you see, we can see these are the methodologies that has been highlighted out here, which was followed for the enterprise data warehousing design for a large corporate model hierarchical models. Enhancing data utilization, authenticity, and flexibility reduce maintenance cost. And limitation was focused on single large corporations. Those are the just a literature overview for this, which we can see in the screen. So moving on to the next slide. So basically, the research methodology, like the enterprise data warehouse data set. Basically, we first do a data preparation and cleansing, and it goes to the legacy OLTP analytics model, where you can see in this image that the tables are getting normalized, chained relationship. So going through that route would definitely have various impacts. And if we have the fact, surrogate keys, decentralized confirmed dimensions, centralized fact tables, it would be much more easier for the dashboard development and identical analytics query. And we did a performance evaluation. Query execution time, refresh consistency, and analytics capabilities also were improved. So, the top customer comparison, the customers remain largely consistent before and after modernization, but low rank customers in the top 10 changed, showing modern shift, while overall sales remained similar. So data processing, data pre-processing, data ensure the reliable analysis by checking missing values, removing duplicates, correcting data types. So data set became clean and analysis ready. OLTP-oriented models before the legacy OLTP model relies on multiple normalized tables with chained relationship and scattered business measures, preserving transactional accuracy but making analytics query complex and slower. Excuse me. The star schema reorganizes data around the central fact table connected to confirmed dimension using surrogate keys, simplifies joins, improving performance for reporting and time-based analytics. So identical analytic query comparison, running the same analytics query shows that OLTP data models are slower due to complex joins and distributed measures, while the star schema provides a faster, consistent, and reliable, reusable calculation such as sales, total, and time of intelligence metrics. So the results for the discussion here is like the OLTP had six normalized tables. After the star schema, we had five tables wherein you can see the details out here, wherein one fact table with four dimensions, which reduced there was a lot of improvement around 17%, which you can see out here on the tables. Excuse me, sorry. So this is what about the results that we got. Definitely, it was a significant reduction, and using the star schema method, we were able to execute the reports much faster than on the previous OLTP machines. So table two, which I'm going to share you, would show the details on the significant improvement on legacy model by reducing the number of tables and relationship and lowering the query complexity. This leads to faster refresh performance and enables full-time intelligence capabilities. So moving on to the next slide, where this shows the entire performance of how the performance was. So if you see, like whenever a report or the table refresh was done, we were seeing a 42% increase, and the total sales and customer name, we got a 39 percentage increase. Like it was faster. So as you see on the screen here, so we were able to improve those. And the conclusion here is performance and migration challenges in legacy SAP business objects environments are mainly due to poorly structured OLTP database, OLTP data models rather than the BI platform limitations. Implementing the warehouse first schema with centralized fact tables and confirmed dimensions significantly improves the performance metrics, consistency, and analytics capabilities. Effective BI modernization requires data warehouse restructuring in addition to the platform upgrades to achieve scalable and reliable enterprise analytics. So the future work that we may have to plan for is validate the warehouse first methodology using large scale enterprise datasets across multiple industries to improve generalizability, implement and test the approach directly within the platform such as SAP Business Objects and SAP Cloud Analytics, including real time. Explore advanced enhancement such as automated semantic layer generation, hybrid lake house architecture. So that is about this particular paper is about. Excuse me.
Thanks for your presentation. Any questions from the audience side? Fine, I have a small doubt related to the idea implementation. So right now, have you simulated the stuff or you have implemented on any data warehousing environment?
Yeah, definitely. We have implemented on the data warehousing environment in one of the customers, wherein these
Okay.
improvement there were a significant
But
level
how
of
many would maybe the files of, because an enterprise level, so how much records and data has been managed in the data warehouse to see the
so,
efficiency of your principles?
yeah, it is like specific to the customer, wherein each individual would have maybe around 50 million records or much more than that. So these depends on the the customer sales and the sales which is happening, and that could have many level of fact tables and dimension tables where these may vary. The number of records may definitely vary, and it's a huge data set that we can go for. It would be in millions that has been implemented for.
Thanks for your time and thanks for your presentation. Let us move on to the next paper, paper ID 213, from Melinda Ramblestone and Varghese Vaidan. The paper title, Empirical Analysis of AI Confidence Methods and Digital Forensic Standards. Over to Melinda.
All right, thank you so much.
Yeah.
Are you able to see my screen?
We can see your camera.
You can see it. Okay, let me just share my presentation. Thank you so much. All right. My name is Melinda Ramblestone, and I am with Dakota State University. And I am here to talk to you today about the empirical analysis of AI confidence methods in digital forensic standards. I've worked on this presentation and this paper with Dr. Varghese Vaidyan at Dakota State University. And so I'm going to go ahead and share that information with you. My methodology and agenda here is on the screen, and you can see the detail on it. We'll go through the problem and the objectives along with the methodology and talk about those key findings, and then finally wrap it up with future work that we're addressing. So on that note, the first thing that I want to highlight, is, I've lost my screen. Hang on. Here we go. I'm so sorry. I apologize about that. So back to the research problem. The research problem that we're dealing with specifically is around AI deployment in digital forensics, and we recognize that it's outpacing the work that's happening in our standards development, and that really is causing an implication in terms of our practitioners being able to use AI in terms of digital forensics, and also meeting the court admissibility requirements that happen in that space. And so there are specific standards and frameworks, but they do not meet the requirements and the structure that are necessary and important to that. So what we did at Dakota State University is take a look at what are those existing standards that we have in place and look to see what the evidence may provide for us so that we can move forward with some research on that. So the first objective that we talked about was explicitly looking at confidence protocols within the frameworks, and we specifically looked at NIST and SWIG-D specifically in terms of the standards. We then wanted to quantify the coverage around confidence, that we wanted to conduct a gap analysis, and then also we wanted to establish a public baseline data set, because that was something that we learned in our research and our literature review, that there was no existing data set that we could use specifically for this problem. So the methodology that we systematically looked at content analysis over the corpus of 165 documents. And those specifically looked at NIST AI standard, NIST CFTT, and SWIG-D. We took a look at them in terms of a confidence framework and a confidence structure, and you can see it here on the screen, the rubric that we use to score those standards and to take a look at them. We also used Prisma in terms of our protocol for document selection to ensure that we were applying appropriate proper rigor, and then also we produced a public data set on GitHub, and that is available for replication. So a couple findings that I want to just share with you all. First and foremost, we learned in this course of this work that there is a 73% gap in terms of standards lacking any kind of confidence measurement protocol, and that is a significant one. If you take a look at the left-hand side of the screen, you can see the study population flow. We looked at 165 documents in terms of digital forensics, and we then identified of those documents, only 27% had any reference to confidence, and of those 27%, only 11.5% had reference to AI specifically. And this is an important piece of documentation because it's not anecdotal, that empirically defines and documents a gap, and that's something that we wanted to build upon. So on that regard, a second area that we then looked at in terms of a finding, in terms of something that was reportable to you all, is this concept of a NIST coverage. And we learned through the course of this, when we compare NIST to SWIG-D, there is a significant difference. NIST being the research organization and SWIG-D being more practitioner-based, that NIST has coverage of 20%, while SWIG-D only has coverage from the confidence of 6.6%. And that's significant because SWIG-D is more commonly used with our practitioners, and that is something that we as a community have an opportunity to build on and enhance, but it is a gap. Third finding that we found is the AI specific protocols. And of this concern, we identified that of those standards that do address confidence, only 11.5% of them specifically talk about AI. And we found this very important because we need that framework, we need that governance, we need that structure and controls for proper implementation around that. And that becomes an issue in terms of AI usage. And AI is essentially invisible to a lot of those standards are not documented. And that is a key finding in that regard. So there are implications to this study and to this research and to this paper that we have provided. I think the first thing that we want to talk about is the practitioners. There's a practitioner implication around this. The lack of validated protocols around AI tool reporting is an important piece because we need to have that AI documentation reported and documented so that our practitioners can properly use and report in the court of law. From a research perspective, we have an urgent need for calibration around uncertainty of our quantification frameworks and helping to close that gap. In terms of our standards body, there's a similar concept that we need to think about, and those standards all need to be updated and to be inclusive for AI, and they all need to be joined and unified together. And this really becomes a cascading failure across one area. There's no one stakeholder group that can solve this problem. It is something that as a community, as a digital forensics community, we need to work through and address. So in terms of future work, in terms of activities that are happening, there is specific recommendations in terms of future research direction. We have identified 4 key areas that we believe and recommend have focus and highlight. First one being development and validation of a confidence assessment framework that it's unified across the industry. Continuing to do empirical study of practitioners in terms of the perception of their use of AI and if it's accurate, if it's valid. Can it be quantified? What are the legal implications of using AI as it relates to confidence? And can we use it when we think about digital forensics in terms of data collection or in terms of evidence collection and presenting it in a court of law? Those are all areas that it's gray and there's gaps in it, and it highlights the need for future research. And then finally, there is an important highlight in terms of expanding this study to the international frameworks. We were small with the selection of our standards, but we believe that we should also be inclusive in terms of other international standards, such as ISO, such as Interpol, et cetera. All of those will help to expand on international frameworks so that it's more unified. Continuing on, in terms of this research, at Dakota State, we are working on developing a unified confidence framework specifically around AI. And that dissertation work that I'm doing in conjunction with my dissertation chair is focusing us in on that. And our intent is to synthesize the standards and then also apply quantitative composite confidence formulas so that we can empirically improve upon the value and the importance of AI. So on this note, I would leave you with these things to think about. We have identified a 73% gap in our standards. It's systemic across the industry. It's not isolated to one particular standard. We have done some of the initial work. I have made my work available out in GitHub so that it is available for us as a community to expand upon. And the last thing that I would ask is that we think about this in terms of the community. We think about how we can improve upon those standard bodies, and we can reach out as a community to do that. So I want to thank you all so much for your time, and I would certainly open up the floor for questions if you have any.
Thanks for your presentation and open to audience for any queries. So it was a good presentation related to the standards of digital forensics. There are many federal-based standards, right? Each and every country has their own forensic standards, and there are some standards which is considered to be like a common standard which can be practiced across the world. So what will be your focus? You'll be focusing only on the international standards, or you have some focus related to the region?
We are specifically focused initially on the NIST and the SWGD standards, and then as we expand it out, we will add. So the international ISO standard, and also Interpol is what we're talking about, and potentially INSEE. We have to take a look at those standards to see which ones we can do realistically, and so we'll probably have to phase it out. But those are the things we're thinking about. I'm certainly open to other ideas if you have any.
Thanks. Thanks for your presentation. Thanks for your time. I think we can move on to the next paper.
Right.
Paper
Thank you,
ID
everybody.
22. Yeah, thank you. Paper ID 221, Nowhere to Hide, Comparative Analysis of Residential versus Cloud Attack Surfaces by the authors Sankalp Lanka, Om Tulsi, Rishik Lanka, and Rani Lanka.
Good morning. Can you guys hear us?
Yes. Can you please share your screen?
Yes. Are you guys able to see our screen?
We can see your browser with the presentation or the full screen. Can you make it a slideshow?
Yes. This is your screen.
Yeah, this full screen. Yeah. Oh, yeah. Okay. How do you stop sharing?
Stop sharing. Yeah, share that one.
This one?
That one.
No, share the entire desktop. And then open the browser.
Okay. Is the full presentation visible now?
Yes, that's good. You have 10 minutes. You can start your presentation.
The internet is filled with background noise. Every minute, bots scan the IPv4 space for easy entries. We wanted to figure out, does an attacker's strategy change when they realize they've hit a cloud server versus a home router?
This question is at the heart of our research. Through our research, we wanted to see if the environment itself changes how an attacker behaves, comparing the massive cloud data centers to tiny residential networks. I'm Om Palsul from Round Rock High School.
And I'm Rishik Lanka from Round Rock High School. Today we will be sharing our study on cloud versus home honeypots, breaking down unique behavioral patterns, and revealing exactly how much each environment was targeted.
And I'm Sankalp Lanka, also from Round Rock. Together, we'll walk you through our findings on attacker intent and the shifting landscape of risk within residential networks.
Before we get into our research, let's quickly talk about the background in residential and cloud security. First of all, there are many vulnerable devices in today's world. Over 70% of IoT devices have weaknesses like bad passwords or poor encryption, and since they're everywhere, they're easy targets for hackers. Because of this, the costs of cybercrime are going up more than 15% every year, and by the end of 2026, it could reach about $11 trillion, making it the world's third largest economy. Another big issue is the cloud, since around 82% of data breaches involve cloud data. As more companies move online, attackers are focusing there too. Due to this, cybersecurity isn't optional anymore. It's essential. But why did we choose this project in the first place? To answer that, one big reason is that there's a research gap that's prominent in this field. There isn't much data comparing how attackers behave in cloud systems versus home networks. Since both environments are widely used today, we wanted to better understand the differences and what that means for security. Another reason is how fast cybercrime is growing, since costs are increasing every year, and it's becoming a major issue not just for companies but also for everyday users. This shows how important it is to study and improve cybersecurity. Furthermore, attackers are constantly changing their tactics. New attack methods keep appearing, which means security research has to keep evolving too. By studying these behaviors, we can better prepare for and prevent future attacks. Our study focuses on two main questions. First, how do attack characteristics differ when identical honeypot architectures are deployed across both residential and cloud environments? And second, does the use of multiple cloud providers reveal diverse targeting patterns that contrast against residential networks across various parameters? Building upon our questions, Our hypothesis was that cloud instances would face a higher volume of attacks compared to their residential counterparts because of the larger attack surface and high visibility of cloud IP ranges. Due to this, we expected to see a much higher frequency of automated scans on those platforms compared to residential connections. Ultimately, this comparison enables a controlled evaluation of how network visibility and perceived target value influence attacker behavior. By analyzing these environments side by side, we can determine whether differences in exposure lead to measurable changes in attack volume and patterns. This approach allows us to move beyond description and directly test the factors driving adversarial targeting decisions.
A honeypot is a decoy system designed to attract attackers. It looks like a real system on the surface, with vulnerabilities that entice attackers, but it is actually controlled and monitored by security researchers. This allows researchers to safely observe attacker behavior without putting any real data at risk. With honeypots, we can identify attackers by logging details such as their IP addresses, the tools they use, and the methods they try in order to access systems. Over time, this helps us track how attack patterns evolve, giving us insight into how hackers are adapting and improving their techniques. All of this data is really valuable because it feeds into improving security defenses, and by understanding how attacks happen, we can even better protect real systems and prevent future breaches before they occur. So our approach was originally a mixed bag. We started by originally planning to use Teapot, an open source honeypot all-in-one honeypot software found on GitHub. But compatibility issues forced us to pivot and build our own custom honeypots from scratch. We emulated 12 target services, including SSH, Telnet, and various Internet of Things interfaces. This gave us total control over our logs and the data we received. To scale this, we used client-side SaltStack automation to deploy these builds across 19 containerized sensors and over 90 honeypots. For the cloud, we provisioned 16 instances across AWS, Azure, GCP, and Oracle. We varied the geographic locations to also see if location impacted the logs we received. For example, you can also see this diagram. Here is where all of our data centers were stored. Simultaneously, we launched our home deployment. We used router port forwarding to expose our honeypots directly to public internet, treating all inbound traffic as malicious. We ran both environments for 21 days to ensure a consistent comparison, ultimately collecting a massive dataset of over 63 million SSH attempts. To keep our deployment consistent, we used a Dockerized sensor core. Containerizing each honeypot allowed us to create a uniform, repeatable setup that could be quickly replicated across all cloud and home instances without manual configuration. We managed these sensors using client-side SaltStack for remote orchestration and FluentBit for logging purposes. We also created a software known as a janitor that sent fake jitters, which are small keep-alive signals, that pushed logs through the pipeline and cleared local memory, ensuring that our individual instances never ran out of storage. All of this data tunneled into a single AWS S3 bucket. Having one central repository made our analysis much cleaner, as we could write our own custom-built Python scripts against one unified dataset. Together, these tools gave us the scalable, automated infrastructure needed to make this experiment possible.
Now let's talk about what we actually found. Our ASN analysis revealed what we are calling a cloud-on-cloud dynamic. The vast majority of attacks on cloud honeypots originated from other cloud infrastructure, meaning attackers are increasingly using cloud servers themselves to launch attacks. Interestingly, our home server received more attacks than our AWS fleet. This challenges the assumption that cloud environments are inherently bigger targets because of their visibility. When we looked at which IP addresses were attacking which networks, the Jacquard index, a measure of overlap, showed very little overlap between attacking IPs across different cloud providers. In other words, different cloud networks are being targeted by largely different groups of attackers. And finally, one of the more striking findings, we identify what we are calling super attackers, which are entities that launch synchronized attacks across multiple networks. This suggests a level of organization that security teams need to be aware of. To wrap up, over a 21-day period, Our home network received attacks at 62% the rate of our cloud servers, which partially aligns with our hypothesis. Across more than 63 million SSH attempts, our log analysis confirmed that attackers constantly rotate and vary their methods. We also found certain credentials like Realtek and Telecom admin appearing exclusively in the residential networks. This suggests that attackers tailor their credential list based on what they expect to find. The takeaway from this is that both residential and cloud environments face a real ongoing threats from different angles, and a honeypot-based research is valuable info for staying ahead of them.
That
Thanks for
concludes
your
our
presentation.
presentation on
Yeah.
cloud versus home honeypots. We hope that this research has provided a clear picture of the modern day threat landscape and how it's shifting away from a broad automated sweeps to targeted and intentional environment specific targeting.
If you would like to discuss our methodology, the specific data points we shared, or our future work in cybersecurity, please don't hesitate to reach out to us at the contact email listed on the screen. We're always open for collaboration and future research insights.
Thank you for your time and attention today. We covered a lot of ground regarding residential risk and developing AI assist tactics. Now we would like to open up the floor for any questions or a broader discussion.
Questions from the audience? I personally like to appreciate your interest and commitment on the cybersecurity research. So your study is quite good and your presentation is awesome. Thank you. Thanks for your time.
Thank you.
Let us move on to the next paper, paper ID 236. Forensic event reconstruction of web attacks using log decoder and rule-based correlation. From Muhammad Noor Yazir Yutomo, Hudan Sutaiban, and Baskoro Adiparatpo. Yes, Mohammed, I think you're muted.
Yeah. Are you
Can you
seeing my
please make it
screen?
as full screen? Yes. Can you please make it as full screen?
Okay. Okay, good morning everyone. My name is Yasir from Institute Teknologi 10 November in Indonesia. Today I will present our experiment titled Forensic Event Reconstruction of Web Attack using Log Decoder and Rule-Based Correlation. This work focused on improving post-incident investigation of web attack by reconstructing attacker activity from server-side log. The main motivation why we conduct this experiment because web attack against web application continue to increase every year. However, most existing research in web security still focus on prevention or mitigation, such as web application firewall or intrusion detection system. In contrast, post-incident investigation is relatively underexplored despite of its important role to understand how, when, and who conduct the attack. Such analysis, however, face another challenge. In web attack, attacker often hide their activity using encoded payload, like the example of the right side of the slide. Because this encoding behavior, existing methods struggle to deal with the situation or the hiding attack activity. So to address this problem, we propose forensic event reconstruction method that include log decoder. The complete proposed method actually consists of 3 stages. The first is timeline recognition, reconstruction, where we combine several type of log like access log, error log, out log, syslog from the Linux server into one super timeline, and then we process to log decoder when we convert or detect any encoded string in the log to find what command hide from the encoded log, and then conduct event correlation to extract important event from the log. This is the key feature of our proposed method. It is log decoder. the lock decoder detects an encoded string and convert it into their original form. The original form then, if there any encoded payload in the log, we edit the original command into the last into the end of the message of the log, like the example in the right side of the slide. Um, After that, we implement rule-based correlation. We implement this using a simple event correlator. This is an open source tools that everyone can download or implement. It is deterministic, easy to audit, and then it the result can simplify or prevent duplication of important event. So it is really easy to use. And then uh, for the evaluation setup, we use a public dataset from Australian Institute of Technology, specifically version 2.0. And then there is several scenario there. We use Fox Web Cell scenario. There are 13 log files merged into one super timeline. In total, there are 400,000 plus log entries from Apache server log, outlog, and syslog. For the evaluation, we conduct ground truth based evaluation. The ground truth itself is published by the dataset. Consists of 28 attack event that actually happen in the scenario. For the metric, we calculate precision recall and F1. This is the reconstruction event from our proposed method. There are 26 event, consists of recon activity, like scanning the web using several tools like Nmap and WebScan, and then exploitation using WebCell. And then the attacker gain the root access, then conduct privilege escalation. Evaluation, we compare the event reconstruction result from our proposed method to the ground truth. We compare it. We compare two things. This is one is the baseline. Baseline is even reconstruction without lock decoder, and the proposed method when where we add lock decoder stage in the event reconstruction process. The baseline achieve high precision but very low recall, detecting only 25% of the attack event. And then the proposed method increased the recall to 82.1%, while precision remain high at 88.4%. The F1 itself, we achieve 85.1%. This shows that decoding process log improve even reconstruction coverage. We also implement our proposed method into two production web server in Indonesian public sector organization. The first datasets the proposed method didn't find any privilege escalation. However, there are some recon activity and exploitation attempts. But in the second dataset, we find complete attack chain, including privilege escalation. These results demonstrate that our method works not only in public dataset, but also in real operation, real dataset, real world environment. In conclusion, the study proposed method for forensic event reconstruction of web attack. The key contribution is introduce lock decoder stage, which reveal hidden attack command in encoded log. The method successfully reconstructs multi-state attack and improve recall from 25% into 82.1% while maintaining high precision. We also uh, put our code in GitHub for everyone or anyone who want to replicate or need it in the future. I think that's all.
Thanks for your presentation. Any questions from the audience? Fine. So in your work, you are going to do the reconstruction of attack based on the logs, right?
Yeah.
Based on the actual logs, you are going to reconstruct the attack and see how it has been happened.
Yeah.
Okay. How many attacks you have done as of now? Because each and every attack has different flavors, different way of execution. So, uh, how many type of attacks or variants of attacks you have tried on this reconstruction?
Okay. For in the stage of rule-based correlation, we we made about 40 rules to we made several rules divided by several common uh, command from Linux like system info or file how you call it there are 40 rules in total, sir. We divided the rule by common comment, like we make categories of the comment, and if the comment match with the decoded log, then it's appear as a important event. And as we make the rule, we implement repetitive iterative adjustment until we get this result. And all the rules are publicly available for everyone in this link.
Thank you. Thanks for your time and presentation. We will move on to the last paper of the session, paper ID 334, Fake Speech, LLM-driven semantic manipulation and voice cloning for realistic deepfake speech benchmarking by Ala Al-Sadi, Amal Al-Mansour, and Amani Jamal. Yes, can you make it as full screen? Yes. You have 10 minutes. Please proceed.
Okay, good morning or good evening, everyone. This is Ala Assaidi, and today I will present my research, Fake Speech Dataset, LLM-driven semantic manipulation and voice cloning for realistic deepfake speech benchmark, which is apart from my PhD thesis. Okay, as an introduction, deepfake are no longer limited for visual or audio manipulation. Recent advances allow alerting the meaning of the speech while reversing the same face, voice, and overlay realism. This creates a more challenge from this deep fake. So we are where the content is semantically misleading, but have some coherence. So most existing dataset focus on a surface level artifact, leaving a gap in evaluation this type of manipulation. So in this work, we introduce a fake speech dataset is a benchmark designed to capture a semantic level deepfake scenario under realistic condition. The research gap where current deepfake benchmark mainly in phase visual or audio artifact, as we mentioned before. Even the closest dataset do not isolate to covered a scenario where the real face same speaker identity, and the visual stream remain unchanged, while only the semantic content of a speech is manipulated. This leaves a gap in evaluating deepfake under realistic semantic level audio-visual consistency. Our contribution, we introduce this dataset as a benchmark for a semantic level deepfake speech manipulation. This dataset, which have a real videos, which is a real video frames and a real audio identity, with a change only the semantic level by using ChatGPT. So the semantic manipulation will be coming from, okay. The semantic manipulation here, we use the same face as we said, and same voice, and different meaning. So here the thread shift from how a person speaks to what the person says, and this is the more challenge in the this era. So how we this is the methodology of how we generate this data set. First, we have using a reference data set in the deepfake, which is most famous one. It's a fake AV celebrity. The fake AV celebrity dataset is a public dataset that use a real content from a Vox celebrity dataset, and the manipulated content with it's use a lip synchronization, edit of a frame, edit of a audio tone, and that's it. There is no touch about the speech or the semantic meaning. So we take this data set as a reference for real content only, then extract the audio from this data set or from these videos. Then this audio we passing in the ChatGPT. We use GPT 4.5. This is the most in the past, to create a phantom read to rewrite with a similar duration and a phantom profile. Why we use a phantom read here? Because we need to the same movement of a lip movement with a word what say it to make a challenge in the detector to detect if it's have a fake content or not. Then we use a clone the original speaker with the 11 lab platform to match the new prompt of phantom read to the original identity. Then at last we have a real frame here with the audio with the fake one, the audio the same identity of a speaker, only changing the semantic. This is our dataset is a fake speech dataset. Okay, this is a dataset description. Here we have 90/70 of a total eclipse with the 40/85 with a real one and 40/85 with a fake one, which have a balance. Here this paper includes or this dataset, include the male and female speaker with a multiple English accent as an Indian accent or Arabic accent or the mother language. Okay, so we have make it a baseline to make different of to evaluate our dataset, and along widely use a benchmark to locate its a difficulty level within the field the chosen dataset. With we chose dataset with audio only dataset and audio visual deepfake to control the compression. We use this dataset to make a comparison. It's a fake or real dataset which is manipulated only audio by cloned speech artifact. Codec fake dataset which also audio only with a neural codec compression. Fake AV celebrity, it's an audio video, which is the reference of dataset. Again, we make it comparison with it. It's use a fake face swap, lip synchronization, voice cloning, and etc. Fake speech, our work, it's the audio video, which is a semantic rewritten within the same speaker identity and the real frame. so the frame with no touches. So here, what is new here? Identity is fixed. So the video frame is a real and unchanged. So not easy to detect if it's a fake content or not. The voice remain the same speaker after cloning. The voice identity will remain the same, and only the spoken message change, while timing of a lip motion is stay aligned. Lip motion stay aligned by using a phantom read strategy. Okay, this is experimental setup and the baseline. Of course, this is a data set with a different range of content and different range of record. So to fair comparison, we make all data sets centralized to 4085 for real content and 4085 for fake content samples. The data set and feature, we separate 70 train, 10% of validation and 20 for testing. And we use a fixed random seed with 101. And the detector here use only audio because some of data set that only audio, so we cannot make a multimodal detection as a baseline. And we use the most famous or the most related one with MVCC to detect the fake content. This is a baseline MLP, and the training hyperparameter we use Adam optimizer with the learning rate is a 1 point of 10 point minus 4. Batch size is 8, cross entropy lows and 10 epochs, and we report a mean of accuracy, Persian record, and F-score. And this is the main result. We got it. This is our data set, which is the red one. And this is the reference data set. It's a fake celebrity, AV celebrity. This is a fake or real and codec fake. And this is the result. As we see here, the high result of accuracy is a fake AV celebrity, which is mean the high result, which is mean maybe the easiest of data set. So if we discuss about the difference of our dataset and the reference dataset as a mother dataset here, it's a fake AV celebrity and a fake speech. Here, as we see, our methodology or our manipulating on the text with remaining all things same, that makes some difficulty on the data set. So that means need to more study about this one. So what say allowed? When only message change, the detector loses 80 accuracy point versus fake AV celebrity. Okay, about other data set here with our data set with a fake or real data set, as we see Persian 0.25 and recall 0.5. So the large quality of variation here, there is a large quality in the variation in the data set of fake or real data set. So that means create inconsistency of increasing a false positive, negative, and lowering. So we cannot generalize any idea from this result. So we need first we cleaning this data set and we take the sample, but after cleaning the data set to control the quality. About other data set, which is a codec fake data set. Here, codec artifact often non-linear dataset have a neural codec manipulation. So the MVCC alone as a baseline not allowed or not available for catch any performance. Every result here by chance only. So about error patterning. on fake speech and a fake AV celebrity. This is a confusion matrix with a true positive and false negative, false positive and true negative. As we see here, the configuration of a fake AV celebrity, which is the reference dataset, and fake speech, which is our dataset. This configuration shows that most model error on a fake speech arise from missed detector rather than false alarm. So Persian exceed recall by 0.12 from 79 to 60 versus 67, indicating the decision boundary that model really misclassifies a real sample as a fake few false positive, but fails to detect many stable manipulation as a false negative. That false negative rate is around to 0.33 on for fake speech, more than twice that fake AV celebrity is 0.50. The interpretation here is the manipulated clips do not sound obviously fake, they sound coherent while saying something different. Okay, what is the implication for this detector? Here, the model prioritized suggested by the paper. It's a combined logistic semantic with the audio or audio tone or process features such as rhythm, pauses, etc., and quantify across a modestly. That means we cannot use only dataset that manipulated on an audio tone or in a frame videos, but we need add more difficulty or add more level of manipulation, which is a semantic level or speech different level that give a dataset more difficult and more challenge. Okay, this is a limitation and the future work. The current scope is English only, with using 11 Lab as a commercial voice cloning system and control generation condition, and evaluating using a lightweight audio only baseline with a low level of features. The next level, and we make it now as a research, is a detailed error analysis, a stronger multimodal detector, a benchmarking with a semantic aware objective and alignment pace losses, broader the language tools and generation setting. So as a conclusion, we have three takeaways here. Fake speech focus on a semantic level speech manipulation rather than the audio or visual edits. Keeping the same frame with the same speaker identity makes the benchmark harder. So the future detector need a cross-model reasoning about the meaning alignment, not only justify artifact spotting. Thank you.
Thanks for your presentation. Any questions from the audience? Fine. Thanks for your presentation. It's really a good work. And by this, we are coming to the end of this session 12. So in this session, we had 7 papers, which collectively with enterprise software vulnerabilities, modern agentic web browsers, and then we had enterprise data warehousing principles, digital forensic standards, various attacks on residential and cloud attack surfaces, and related to forensic event reconstruction, at last, fake speech. So we have multiple platforms of discussion, and I think which actually given a wide idea for all the participants. So by this, I'd like to conclude the session. Thank you all for your time of presenting this your research work, and over to the organizer. Thank you all.